Good afternoon to one and all present here. One announcement. The participants, those who are stay back here, the parallel session will be held on Data Science Lab, Computer Science Block, VMK Engineering College. And parallel session 3 will be held on iTech Lab, Administrative Block of VMKV ESC. Those who are, the participants, those who are stay back here, that people belongs to auditorium or some other blocks. Here only. Those who are having a PPT are going to be present on a PPT. Do you have a pen drive? You just copy it from that. Okay. The session is going to be start. I'm very humbled to welcome Professor Dr. D. Vinod Kumar, Professor and Head Department of Biomedical Engineering, Vinayaka Missions Engineering College, Salem. Now I request you to occupy the stage, sir.
Good afternoon, everyone. I am Dr. D. Vinod Kumar, Professor and Head of Biomedical Engineering, Vinayaka Missions Kirupananda Variyar Engineering College. It's a privilege for me to introduce today's resource person, Dr. Aruna Kumari, who is currently serving as an Assistant Professor and Coordinator of the Department of Chemistry, Oxford College of Science, Bangalore. Dr. Aruna pursued her bachelor degree in chemistry from Tumkur University, Tumkur in the year 2009, and her master degree in organic chemistry from Korea University, Shimoga in the year 2011. She received her doctoral degree from Bangalore University in the year 2017. She visited Core Facility Center for Photochemistry and Nanomaterials, Department of Chemistry, GNU, South Korea, as a visiting professor in the year 2023 to learn and carry out the research on pulsed laser synthesized catalysis for energy and environmental application. Her research interests span a broad spectrum of photochemistry involving energy, environmental, and material chemistry fields. She has authored more than 25 research articles in the international peer-reviewed journals and has authored several review articles and book chapters of scientific repute. She has delivered several invited lectures at international conferences and academic institutions. Her current research interest includes the synthesis of metal oxides and its organic and inorganic hybrids for energy and environmental applications, photocatalyst, organic transformation, and developing advanced oxidation process, including phenton and photophenton process. Now I welcome her to deliver the lecture.
A very good afternoon to one and all present here. I know it is very difficult for all of you after a post-lunch session. I know some of you may sleep, but I could say that if you tell me that you are all belonging to master's or research level, I can change my presentation based on your requirement. So can you please raise your hands, how many master students are here? MSc masters? Research scholars? From chemistry background? Oh, then remaining all from bio background or what? Okay. So I'll make very simple in such a way that the one who are all sitting here, they're able to understand what I'm going to present today, what I have done in my research career, because I believe I don't want to waste my energy in just explaining my research unless until it will reach a bit of it for you. Okay, so today my presentation includes two parts. One is sustainable energy Another one is biomedical application. So I have created a material of heterostructure which is titanium based. So why we have selected titanium? Titanium dioxide is the one material which I have used predominantly throughout my research career. The titanium dioxide is not a new material at all. It was there from many years ago, where mechanical engineering, biological people, all of them, they used to it. So what made me to select this titanium dioxide? One day, I randomly, like without any clue how we joined for research, like that I also joined for my PhD. Then that time we are just sitting and we are trying, usually girls what they do, they try to use cosmetics more. So usually being a chemist student, we have a idea that what chemicals are there, whether parabens or something is there which will harm for my skin, like that we usually check. So when I was checking that, every time I used to get two oxides. One is titanium dioxide, another one is zinc oxide. So why they used to use that much predominantly in the cosmetics? Because mostly when we use the sunscreen, these two material have an ability to abstract the sunlight and they protect our skin. So that is how I started, and then I also have a biological background. So I want to use biological mixed with the chemistry. So when we want to do the research, PhD is usually for the society purpose. So as we know, we all work for the community. So when we see that, we have every year this sustainable development goals they will keep. For every 5 years they release certain goals. So among that, the water scarcity and the other one like energy, these are the two critical points which we supposed to do research. So when there is a need, we have to do research. So these are the two areas where we have a predominant need of research. So that too, particularly having a fresh water, which is very not easy to get the fresh water, because everywhere we have a contaminated water. So to address this problem, we want a material in such a way which should be safe, little less price, simple process should be there, and reliable. That means we can rely on it again and again even in our future, and robust, and it should be a one-point source. So for this, we wanted to utilize the solar power also. So based on this concept, like we all know the photosynthesis, where it uses light, carbon dioxide and water, it produces sugar and the oxygen which we all will intake. So similar process even it will happen in the photocatalysis too. So in the photocatalysis, see, being a teacher, for me it is very difficult if someone uses a mobile phone or something when we are talking. So from the stage, I feel it is very disturbance. So can you please turn off your phones? If you are really interested, you can go out and you can use your phones. So photocatalysis is the one where we use energy and the environmental, we can address both the issues. So based on this, what exactly they do is, I have used this semicolor mechanism for photodegradation and the water splitting. Along with this, we also used for the biological application. So what is the basic principle behind this catalysis is, you can imagine this has a titanium dioxide. Inside, what exactly the process will happen. So once the sunlight fall on a titanium dioxide, it will absorb the radiation. Once it absorbs the radiation, the electrons will go from one state to another state. During that state, it gives so many side reactions where some reduction, oxidation, recombinations, so many processes will happen. So these processes we are utilizing for different applications. Some of this process we are using for water splitting. Some of this process we are using for wastewater treatment. Some of this process even we are using for the biological purpose. So when we have to select a photocatalysis, what exactly we see? We see it should be low cast, direct band gap. All I can say is it should be cheap and it has to work under normal sunlight because we don't want to give any external light source for it. So that is where the titanium dioxide plays a very important role. So what exactly it do? Titanium dioxide will take the light and it will generate the hydroxyl radical. So this one is very stable, non-corrosive, environmental friendly and even bio-friendly, and it has the appropriate band edge position so that we can do the catalysis reaction. For example, if we use the sulfides or other things, then it may undergo corrosion or the reproducibility of that material might not be good. So, but it has a two drawback. One drawback is it will work only under UV light, but our sunlight doesn't have more UV light. It has only 5% or 7% of it. But we want to make use of it under sunlight. And whatever the electron will go, it gives, in the previous slide what I showed, like that it will undergo series of process. So what exactly will happen? It will come back very fast or it will give a side reaction. So we cannot utilize those reactant species what they have generated during the course of photocatalysis. So to avoid this, to overcome this, we have used so many strategies till date. So we usually dope something, or we do surface modification, or we mix with the another semiconductor, or we do morphological modifications. Like this, we do so many things. So among this, I particularly worked on the coupling with the other suitable semiconductors. So that too by forming a heterojunctions. So when I wanted to do the heterojunction, I used a sol-gel process, because sol-gel process is the one where we get chemically pure compound. If we use a hydrothermal or something else, then we can get the other element inside the other, like nitrogen or carbon or any other thing might be doped during that process. So we usually, if we want to go for a pure material, we usually select the sol-gel process. So when I selected the sol-gel process, then I have used that, we have mixed with the other semiconductors like ZNO or the SNO2, then we did the ball milling. So when we did the ball milling, we usually get the heterojunctions like this. One semiconductor mixed with the other semiconductor, we get the heterojunctions, so that I can improve the visible light activity, and even I can avoid the recombination pattern of it. So this is what I expected. So I have taken one TiO2 and one ZNO. I want to generate titanium dioxide of one phase and the ZNO of another phase. Research is always unexpected. I expected the two phases like this, but I got ternary phases like that. So I have taken one titanium dioxide phase, but I got the other one. So what exactly that other phase? So titanium dioxide phases, whatever we talk, one is anatase phase, the another one is the rutile phase. So most of the chemistry students, they might have know that monoclinic, that different kinds of solid state when they are reading. So they may have come out of, they may have a little idea about it. So anatase is the one which has an octahedral geometry. You can see the anatase and rutile both have an octahedral geometry, but the way they are arranging makes the phase. So when they arrange like this, we got anatase and the rutile. So in the anatase, it has been a cross way and the side way, but in a rutile, it has been arranged only in the cross way. So when I did the ball milling, what exactly happened? During the process, the anatase has been converted into rutile. So this one usually we used to do. Why it has to happen? Because as the temperature increases, their phases will change. So when I did the ball milling, it produces the enormous amount of heat that converts the anatase phase into the rutile phase. So this we have identified using the phase characterization by using powder X-ray diffraction studies. So from the powder X-ray diffraction studies, what I have taken is pure TiO2 and pure ZNO. When we have done the ball milling, we have got the ternary complex of it. So we have also tried for SNO2. When we have tried for SNO2 also we have got. So from this we identify that this transition is usually because of that ball milling process. So how much quantity it is there, how much percentage of anetyl is there, how much percent of rutile is there, that is we are so curious. So why are we so curious about it? Because worldwide titanium dioxide has a commercial valuable, that too in that we usually use Degussa P25, which we usually call as DP25. So what exactly this DP25 is, this has an appropriate ratio of anetes and the rutile phase. So it has 70% of anetes and 30% of rutile phase. So I wanted to know in this composition whether I got that phase, I got that ratio or not, because that ratio is worldwide accepted as a best material. So I want to know whether I got that particular ratio or not. I wanted to cross check. When I cross checked, I didn't get. So mine was like 50% of anetes was there, 50% of rutile was there. So I was not able to get that particular composition. But we have developed some material, so we wanted to make use of it. Then as usual, since we are working under photocatalysis, we check for the band gap. So when we check for the absorbance, we got a visible light absorbance, then we calculated the band gap. So band gap is almost come to the visible region, slightly shifted to the visible region from the UV region. Then we have done the XPS studies on the surface, what exactly is there. So from the XPS studies, we understand there is a interlink between the titanium and the zinc, and they partially shifted. So based on the shift, we are able to know from where to where the electron transfer is happening on the surface, because photocatalysis is most prominently happen on the surface. Then we have tested for oxygen, so how many different kinds of chemical composition we have. When we come to know, there will be pure composition in TiO2, ZnO and SnO2, but when we have done the heterojunction or ternary junction, that that chemical composition has been mixed with the so many varieties of subcomposite. It is not a pure chemical nature is there. Instead of that, we have a different chemical nature instead of one. Then we have done the TM analysis just to know the particle size, because particle size matters a lot in the surface. And we also done the HR-TEM analysis, so to identify whether the phases are there or not. So we concluded the heterojunction is formed. Then we wanted to go for the photocatalysis study, so we have selected the para-nitrophenol. So that para-nitrophenol is very difficult to break compared to the 2-nitrophenol, because it has a two kind of hydrogen bonding, intra and inter-hydrogen bonding. So then when we have done that under UV light and the solar light, it has been given a better result both in UV and the solar light. So based on that, we have developed the mechanism parts from where to where the electrons will go and all those things, and how it will work in the UV light and the visible light. Then finally, since basically I'm an organic chemist, I will be interested in degradation pattern, how the degradation was happening. So this one we have GCMS analysis we carried out. Then based on the GCMS analysis, we are able to predict this mechanism of degradation, how it has been degraded, and then at what time interval, what intermediate has been performed, at what ratio it is there, that also we try to analyze. And after that, till now I have done about the ternary heterojunction. Then that particular time, the whole world is trying to work on the black titanium dioxide. Usually titanium dioxide is white material, but what happened that particular time, they usually need a black coloration in that. So why we need a black color? Because black body will absorb all radiation. So it's not only the white, color, because black is meant for the whole light absorption. It will absorb more, correct? So black body radiation is nothing but the absorbance of a light will be more and emittance will be the less. So we also want a black titanium dioxide, which will work as we predicted. This will work under solar light. So when I got an opportunity to visit the GNU, from morning onwards you might have heard the people who work in the pulse laser. So when I got an opportunity to visit over there, so there they are working on this particular topic. So there unexpectedly what we have done, we have just taken a titanium dioxide, we just kept it in the pulse laser. For 1 minute, 2 minutes, 3 minutes, the color transition has been changed. It is turning white to gray, gray to black. Like this, it will be keep on changing. Within the span of 5 minutes, the complete white material has become the black material. So why is it happen? Like to identify that concept, I worked there for 2.5 months, and then finally we are able to identify what exactly it is happening over there. So usually when we irradiated the pulse laser, what will happen? It will take out some oxygen from it because we are hitting with the light. So when we hit with the light in the titanium TiO like this, it will be, particular phase will be there, arrangement will be there. So from there, oxygen has been removed. So since the oxygen has been removed, the neighboring titanium wants to accommodate its stability. So to accommodate its stability, what exactly it has done, it has been reduced to its Ti3+ state. So this Ti3+ states and the oxygen vacancies together usually forms a new energy level, new energy position, that from there the electron transition will happen. That is why it is coming to the black color. But usually converting from rutile to black titanium, rutile to black TiO2 is easy compared to anatase. This we are able to achieve using the pulse laser. So what exactly happened when we have done with the pulse laser? This has that kind of geometry, anatase phase, where the oxygen will get cut and it will create a vacancy, and that vacancy it has to get adjusted, so it will change its phase to anatase to rutile few of it, and still it will induce the black color. So when we have done this, what exactly happened? So when we keep on irradiating with 1 minute, 2 minutes, 3 minutes, the rutile concentration is also increased and we are able to get the black color. So I believe that particular time it is very good material for photocatalysis or electrocatalysis. We can do for water splitting or something else like that, I believe. Because black TiO2 was in a particular zoom out of it. But what has been turned out for me is, my material didn't work for photocatalysis, my material didn't work for even electrocatalysis. How much ever I try, I'm not getting a better result. I mean, we are not getting the better result. So then, to characterize that, we went for morphological studies and we have done the XPS studies. We have even done the time result spectroscopy, just to know whether at what particular level that band gap, that vacancy, that band gap has been formed. So then we have done the reflection electron energy loss spectrum, which we usually call EELS, which is very much appropriate to calculate the band gap. Not the regular UV. So when we have a defects, we usually go for this kind of analysis. So here we particularly get a band levels. So where we have a valency band, where we have a conduction band, exact band gap we can get. So to calculate the band gap, I have used the two techniques. One is EELS, another one is UPS, and this is what the UPS spectroscopy result. So where we usually calculate the VMRF functions and all, and after calculating this, we wanted to go for the applications. When we go for the application, as I mentioned, I didn't get for electrochemistry or photochemistry. So then we shifted it to the biological application. So why we have shifted to biomedical application? My material is not at all active, not much active in the visible region. It is active in the near IR region. So since it is acting, its absorbance is more in the near IR region, we believe that kind of material will be very good for cancer studies. So this cancer studies has been done with the help of Satyabama Institute. So there we have done cancer studies where we have strained the different kinds of dyes like AO, CB and all. And then finally we also predicted the mechanism for it, and we find it out that we have many material, but the one which is in the middle, like black titanium with the 3-minute, which is having a particular composition, has been worked out as a best material for the cancer studies. And during the process of mechanism, we identified that the main reason for the biological, that cancer studies, is production of the hydroxyl radical when we keep under the sunlight. So a portion of it will absorb the visible region, and because of the stress and stress induced by that hydroxyl radical, the cells are going to die like this. We are able to predict the mode of that cell death in the cancer cell. So this is all about my presentation, and I'd like to thank Vinayaka Mission for giving me this opportunity, and I also thank Professor Choi for giving not only one time, he has given me 2 times option to visit his lab and to carry out the research, and I'm happy to say in most of his project I was a part of it. So either I will be in a part of mechanism prediction, or either I will be in a part of material designing. So even though I don't have an independent lab, he has given me the wide varieties of opportunity to being with his lab consistently, being in India. So thank you, Choi sir and Professor Choi and Anbalagan sir for giving me this opportunity, and I would like to thank all of you so kindly being sitting here and listening to me. Thank you.
Thank you, ma'am. Dear participants, do you have any queries? Any clarifications?
I know most of you have not understand anything.
Good afternoon, Professor.
Thank you.
Your presentation is very nice. Especially you are working in black
Can
titanium.
you speak little louder?
Yes. You are working in black titanium dioxide.
Okay.
That work is very impressive. I have some few suggestions.
Okay.
Shall you please go to your XPS slide? I have some small doubt.
XPS you want to?
Yes.
Which XPS? This one?
No, the comparison of titanium, zinc oxide.
And the black titanium dioxide?
No, before that.
Okay. This one?
Yes, exactly.
This one or this one?
No, O1 spectra.
Okay, oxygen.
Spectra.
Okay.
In titanium dioxide, oxygen 1 spectra, there is no peak is observed around 532.2 electron volt. In your case, zinc oxide, you are having one more peak. This might be due to the formation of any oxygen defect or any other formation.
I didn't get your question. Can you please speak?
No, actually, in ZNO XPS, you are getting one more additional peak is around 532.2 electron volt. There is no peak which is observed in titanium dioxide.
Yes.
This might be due to the formation of any oxygen defect or any other defect in your material.
Yes, I'll answer for this. So this actually when I have taken TiO2, I have only one phase, that is anatase. So XPS is the one which tells us about the chemical environment, how many different chemical environment I have. So here everything is too pure, so I have one particular component for it. When I have gone for the ZNO or TiO2, ZNO oxygen attached to Ti I will get, oxygen attached to Zn also I will get.
Fine,
so I have 2 over there. Okay. So here also SNO2 and this one also similar.
Okay, fine. Thank you.
Okay.
Thank you, ma'am. Any questions from the audience?
Okay.
Thank you, sir and ma'am. Now I'd like to invite Dr. M.L. Aruna Devi to honor Professor Dr. D. Vinod Kumar.
And before that, I will like to thank our ma'am. On behalf of the iNEEBA-2024 team, I want to extend our heartfelt gratitude for your insightful and engaging lecture at this conference. Your expertise on this topic provided valuable perspectives and sparked meaningful discussions among the attendees. Thank you for sharing your knowledge and contribution to the success of the event. Thank you, ma'am.
I would like to invite Dr. Vinod Kumar sir to honor Professor Dr. M.L. Arunadevi. Thank you, sir. Thank you, ma'am. Now the parallel session 1. Session jury is Dr. B. Sendil Kumar, Associate Professor, Vinayaka Missions Kirupananda Variyar Medical College and Hospital. May I invite you, sir? Oral presenters, OP, ESE 13. Once again, I'll repeat. Do you know the paper ID OP ESE 13, R.L. Bhuvanish and A. Kadiravan. The next presenter, OP ESE 14, S. Geeta Lakshmi, B. Darshana, V. Kesavi, S. Saumya. Get ready for next presentation.
My name is Bonish. I am from Department of Chemistry, Beltech University, and my supervisor's name is Dr. A. Kadiravan. Today I am going to present about AA active TP derivatives for copper sensing and left image. So first, biological importance of copper. Copper 2+ is very important for human activity. That is, when it is low, when the amount of copper is low, it causes Parkinson's disease and Menkes disease. When it's high, it causes Wilson's disease and ALS and several other neurological disorders. So it is very mandatory, imperative to determine and regulate the amount of copper that is present in our body. That is why WHO has recommended limit of 31 micromolar in drinking water. So there are many analytical techniques such as atomic absorption spectroscopy, IPCMS and various other chromatographic technique that we use to determine the amount of copper present. But these do come with several disadvantages such as time consumption, requirement of sophisticated instruments, laboratories, expertise, and also large volume samples. So that is why scientists have been working on for the past 2 decades to develop chemosensors. So chemosensors can be classified into 2 types, colorimetric and fluorimetric. Colorimetric, when the analyte is introduced, it induces color change, whereas in fluorimetric, when the analyte is introduced, it will induce change in the fluorescence intensity. Here in this context, we are just going to see about the fluorimetric sensor that we have developed. So basically, the background before going into that is Jablonski diagram. I don't know if people are here in the chemistry background, so I'll just make it short, I'll explain it. So when you excite a molecule in the ground state, it will go from the ground state to the excited state, absorb and go to the excited state in 15 seconds, 15 time seconds frames. And there occurs many internal processes such as internal conversion, and from there are two pathways it can come down to the ground state. One is radiative pathway and the other one is non-radiative pathway. For the non-radiative pathway, there are many processes that can occur. One is intramolecular rotation, another one is intramolecular vibration. Together they can be called as intramolecular motions. Whereas in the radiative pathway, when you excite a molecule, it goes to the excited state and comes down just by emitting light, either as fluorescence or phosphorescence. So the typical fluorescent molecule in its solution state, it applies. The Jablonski diagram, the theory applies. It will be emissive in solution state, but whereas in solid state, it goes to a process of pi to pi stacking, so it is non-emissive. So Mr. Tang, Professor Tang in 2001 came up with a solution wherein when a TPE molecule in solution state, it is non-emissive due to free phenyl which will rotate, that I explained before, intermolecular rotation vibration. So it won't be emissive, it just loses energy that way. But when it is aggregated, it will induce the restriction of intermolecular motion, thereby it will come to ground state only by emitting via light. So we have taken that, inspired from that work, we have designed a molecule. The theory behind it is when water is used as an solvent, it will aggregate the molecule and it will restrict molecular rotation, thereby it can only come to the ground state by emitting light. This is called aggregation induced emission. So this is the scheme that we have used. We have used a TPE aldehyde, and this receptor site has been specifically designed by our group, which is very highly selective for copper. And for copper, we have already in our group, they have published analytical chemistry dyes and pigments paper using this receptor. So when we add water, when we be varying the water percentage, as you can see visually, at 90% the aggregates, it is highly emissive. So spectroscopically we have characterized, you can see that at 90% water percentage, it is highly, fluorescent intensity is high. So when it changes from the solution state to aggregate state, you can easily see that. And so we measured TCSPC measurement, whereas in the 0%, that is in solution state, the lifetime is very poor. But in the 90% aggregated state, the lifetime is increased. The lifetime, not only the lifetime is increased, but also the radiative, non-radiative decay has changed. Here in the non-radiative decay, that is the rotation is hindered, that is shown in the parameters itself. That NR is a radiative or non-radiative decay constant, has been reduced. And we have characterized the morphology of the aggregates, that is from solution state we have taken DLS, and also we did a simple Tyndall experiment. As you can see in the 90% aggregates, the scattering is more visible. And also we did same measurements, it is characterized to be spherical aggregates, and in the TEM measurements, the average particle size is determined to be 90 nanometer, and it's also monodispersed. Whereas for the application part, we designed this for copper sensor, so we utilized it, and it is highly selective towards copper. As you can see in the plot, that copper has the highest quenching efficiency. In the insert image also you can see that only copper has quenched the fluorescence intensity, not any other cation. And also we did anti-interference study, because since if you are going to use this in a practical application, you can't just say my sample should only contain one cation, right? So it might contain various cations. My probe will specifically detect only copper. So we did anti-interfering studies, and the quenching efficiency of copper is not reduced as expected. And the theory behind it is we optimized the structure. As you can see, this is the MESP diagram. The high electron density is in the pyridine unit. That is, this can be the binding site for any metal ion. So here in copper, so we optimized the structure for it. And when we introduced copper 2+ into it, the dihedral angle is reduced. Therein, it was reduced to 3 degree from 31 degree. So it is a huge. So we did experimental, and the experimental evidence is shown here in the DLS. The polydispersity index, that is which confirms if the molecule is monodispersed or polydispersed. As you can see here, when the copper is introduced into the aggregates, the polydispersity is decreased, thereby proving that complexation. And also we did spectroscopic characterization, wherein this is called MI scattering. Photophysicists might know this. In MI scattering, when the aggregates are formed from the monomer, that is an MI scattering. So when copper is added, there is a reduction in the Mi scattering. So this is also one of the proof which supports our claim. And we also did a usual energy level diagram. As you can see, this is the HOMO-LUMO of the standalone TP molecule, and this is after the introduction of copper, that analyte. As you can see, the energy difference between the HOMO-LUMO has drastically reduced. This is indicating that there occurred an electron slash energy transfer from my probe to copper. That is the case of fluorescence quenching. And we did quenching studies. As we increased the concentration of copper, the fluorescent intensity decreased with a linear range. And also we did, usually we found out the LOD to be 83 nanomolar, which is threefold the times higher than required from a WHO recommended limit. And the quenching studies, we also did Stenwalmer plot, which will prove that complexation has occurred in the ground state, since that is an upward curvature. And also we found the association constant to be 8.99. This is the driving force for better LOD. And the effect of pH, since we are going to use this in practical applications, we just have to determine what is the effect that pH causes here. As you can see, in the acidic condition, the fluorescence intensity is very low, whereas the quenching efficiency in the practical region, that is from 7 to 8, it is not affected that much. This might be due to, since our molecules contain pyridine, when we change the when we change the pH value, acidic nature will affect the fluorescent intensity. And also the real-time application, we collected samples such as rainwater, tap water and pond water. We checked for the copper percent in it, and we injected, and we found the required to be 99.73% recovery rate, which is very good. RST is also very good there. And in comparison, these are the other TPE molecules that have been published, one in Photochem A and Journal of Molecular Liquids, and another one in Sensors and Actuators, Journal of Molecular Structures. These are all TP derivatives that has been published in the last decade. And our molecule has a better LOD, and the driving force is the association constant behind it. So also we did, as a bonus, we did LFP imaging. Since our molecule is green, this does not have any interference from the background. So we did LFP imaging. As you can see, first level, second level and third level. With the normal fluorescent, normal fingerprint LFP imaging, we can only go to the second level, but wherein this LFP imaging, you can go to the third level and study about it. So it is a potential candidate in forensic investigations. And the conclusion is, we have developed a novel TP derivative. The LOD, good LOD and selectivity towards copper, and the mechanism is delineated to be complexation, deaggregation, and the static time quenching due to that we found out from the TCSPC decay experiment. And we also did real world practical applications with a good recovery rate. And finally, promising, it is a promising candidate in LFP imaging. That's my professor, Dr. A. Kadiravan, and I thank Vailtech for scholarship, NEHU for the synthetic assistance, and IIT Madras for the collaboration in this project. Thank you.
The topic is open for discussion. Any queries? So yourself Kadiravan, right?
No sir, Bhuvanesh, that's my professor.
Bhuvanesh, okay. So Bhuvanesh, you told about the probe, right, which is available for detecting.
Yes sir.
Is this probe they have checked out with other than copper?
Yes sir. As you can see in the plot that I have shown, with other cations, among 10 cations, only copper, it can only detect copper, specifically detect copper.
Specifically detect only copper?
Yes sir, even we checked it with other cations. For example, zinc, copper, cobalt, everything, it can only detect copper.
And can you tell me what is the forensic relevance for this fingerprinting?
Forensic relevance, so for example, when you are using normal forensic powders, it is toxic in nature, and also there will be high interference from the background. For example, you can just take a picture of your fingerprint laid on any surfaces. In this work also we have tried with various surfaces. When it is fluorescent in nature, there will be a very less interference from the background. Since we are using UV torch, it will be somewhat violet UV light. It will show some sort of interference from the background. Since it is fluorescent in nature and green emissive, it does not have any interference from it.
Okay, good presentation. Thank you, sir.
Thank you, sir. Next participant, OPEAC 15, Idumpan Jaishankar Raja Sulaiman. Next participants, OPEAC 16, Pon Niveta A. Lalita Patel. Next participant get ready. OPESE 18, Sankara Narayanan and Ananta Kumar. See.
So good afternoon one and all. Myself Ponniveta, DST Inspire Fellow from Department of Chemistry, Avinashlingam Institute. And I am here to present on innovative wearable superhydrophobic textiles crafted from silica, sand, nanoparticles and eco-friendly modifiers for enhanced anti-wetting applications. And here are the contents. To begin with, superhydrophobic surfaces. They are extremely water repellent and they show water contact angle above 150 degree and the droplet slides off below 10 degree sliding angle. And coming to textiles, this enhanced water hating behavior delivers outstanding applications and it also increases the lifetime of fabric, and it is applicable to daily wearables from military to medical applications as well. And it also can be customized for various applications like self-cleaning surfaces and oil water separation, wearable garments and multifunctional textiles, etc. However, this field of interest finds drawbacks like mostly fluorinated compounds which are environmentally toxic and non-degradable. They are finding most utility, and therefore there is a need to introduce eco-friendly modifiers in superhydrophobic textiles for wearable applications. So that's why in the present research we make use of an unconventional silica source which is Shetala sand, and this sand is found to have a greater silica percentage, and we utilize this sand for preparing silica sand nanoparticles using ball milling technique, and here we have optimized the BPR and milling time to arrive at maximum size reduction using a 3-level 2-factor central composite design. And after that, the prepared silica sand nanoparticles were effectively incorporated in the superhydrophobic coatings along with the eco-friendly modifiers like stearic acid, polycaprolactone and silicon oil. And the prepared coatings were characterized, tested for their self-cleaning activity, durability. It is also proposed for oil-water separation using an indigenous setup, and at last we have tested for the electrochemical behavior of these textile materials by assembling as a symmetrical supercapacitor using gel electrolyte, and then cyclic voltammetry is recorded. So here are the response surface methodology results, and we found that the trial number CST5, which is run at BPR 20:1 and for 10 hours, yielded the minimum, that is the finest particles, which is as low as 26 nanometer in crystallite size. And these particles, and this methodology also proved that BPR, that is ball to powder weight ratio and time, to significantly affect the particle size. And these, the finest particles were taken for superhydrophobic coatings. And we know obviously the pristine cotton is extremely hydrophilic. After modifying it with silica nanoparticles, it still remains hydrophilic because silica surface is hydrophilic in nature. And however, after the final step of modifying with silica nanoparticle incorporated polymeric composite coating, we could achieve the superhydrophobic surfaces, and the coated surfaces were found to be extremely hydrophobic, and we could achieve a maximum contact angle of 158 degree. And these surfaces were tested for their anti-wetting performance. We found an extended anti-wetting life, that is the dyed solution showed it is not permeable across the weaves of the cotton fabric even after a long time till the droplet water evaporates. And this table shows a comparison of the respective blank trials, and we found that the proposed coating has a synergistic effect from each of the ingredients, and that's why we are able to achieve this maximum water contact angle. And we have actually characterized the coated fabric with respect to the uncoated ones, and here is a sample. And this orange one shows the coated ones, and this is the uncoated ones. We are able to achieve the similar whiteness level even after coating, and 3D optical profilometer results showed an increase in roughness after coating. and this contributed to hydrophobic behavior. And the FVSM result substantiates the result that is micro-nano roughness structures were seen on the coated surfaces, and the coatings were also found to be uniform, compact, and there is no closure of the crisscross junctures. Therefore, we found the coatings to be breathable and of lightweight. And this TGA-DTA curves showed an additional weight loss between 400 to 800 degree, which is attributed to the mass loss from the decomposition of the coatings. And the additional peaks in FTIR compared to the uncoated ones shows the successful incorporation of the polymer composite coating. And the coated surfaces were also tested for their durability. They can withstand more than 5 detergent washing cycles and the acidic and alkaline pH. We also found the surfaces to be self-healable, that is, they regain their superhydrophobicity after heat treatment. And to test it for practical applications, we proposed this oil-water separation, and we found that using an indigenous setup, we are able to achieve more than 90% separation efficiency, and this efficiency is reproducible after 5 separation cycles as well. And nowadays, the smart e-garments are gaining more attention, and that's why we have proposed this textiles as a wearable conductive coating so that it can find future application in e-garments. So here we have run the cyclic voltammetry study for the developed coatings and compared this with the RGO coated fabric, RGO being a standard electrode material, and we found a comparable results between the two CV curves, cyclic voltammetry curves, and this is attributed to the other metallic particles present in silica sand nanoparticles and its crystalline nature. And it also prevented the rapid leaching of active material so that we can get sustained behavior. And the CV curves are quasi-rectangular in shape, which conform their electric double layer capacitor type behavior, and it can be proposed for future application in wearable textiles. So to summarize, we adhere to the SDG goal 12, that is responsible consumption and production, by preparing silica sand nanoparticles and incorporating it in eco-friendly superhydrophobic textiles, which can be applicable for future multifunctional wearable coatings. And these are the references and acknowledgement. I acknowledge Bharat Ratna Professor CNR Research Center, Avinash Lingam Institute for all the instrumentation facilities and Inspire Fellowship for the financial assistance. Thank you.
The topic is open for discussion. Any queries from the participant side? Your silicone nanoparticle, you were telling that it was resistant to what, up to what pH level it was resistant?
So 12.
Up to 12 it was
2
resistant.
to 12. Acidic 2 to 12.
2 to 12. So you have to coat this, and what will be the medical application if this is applicable in market?
So medical application so far we have not tested, but we can propose this for UV protection activity because silica basically have this high UPF factor. So we can extend this for protecting against ultraviolet radiation.
Okay, okay, good presentation. Thank you.
Thank you.
Thank you for your presentation. Next participant, OBEAC 18, Sankar Narayanan and Ananta Kumar. Next participants get ready, OBEAC 19, Mohan Jagan and SP Vijaya Chamundeshwari.
Good afternoon, and all present here. Myself Shankar Narayan Karthikeyan from SRM Institute of Science and Technology, Katangaluttu campus. So today I am present on the title about enhanced pseudocapacitive two-dimensional NTO based high density supercapacitor. That NTO is sodium titanate oxide. That titanium oxide is doped with sodium. So first we have introduction about supercapacitor, and then why we choose the supercapacitor, and then classification of supercapacitors, then why metal oxide, we have worked on the metal oxides, then we choose sodium titanate, then highlights of my work and preparation of nanomaterial, then characterization studies, summary and future works. So as we know, the energy storage nowadays is very equivalent weights. that we have to battery and supercapacitors is comparatively very good to give power density, energy density. So we have electric energy storage device that is store, release energy and reversible like absorption and deabsorption of the ions and interface between electrode and electrolytes interface. Then there are three types of supercapacitor, that is electric AA capacitor and pseudo capacitor and heavy capacitor. Nowadays that capacitor is collaborate with battery also, that is means supercapacitor also working. So why supercapacitor? So why means that we have first we need to know the energy storage. So a lot of people working as battery. So now supercapacitor, why means that is cost effective and long life and eco-friendly, excellent power density and fast charge discharge. So comparatively next we have to move on to classifications. Here we have three types of classifications. First we have that is electric AA capacitor that stores charges electrostatically, and then second one is pseudo capacitive that is stores charge electrochemically, and then both we have to hybrid, we have to capacitor that stores electrochemically as well as electrostatically. Now they are working as hybrid capacitor. So that is asymmetric or pseudo capacitor. Both are working as rechargeable battery type. So now why you choose the metal oxides? So here we have choose the metal oxides for energy storage devices. That is we have to layer type material that we have variety types of oxidation states, but we have to charge transfer process taker. So then we have to take the metal oxides that is lithium, sodium, potassium binding together to metal like titanium that will form as a doping like sodium to enhance the capacity. Why means that sodium will occur to binded with titanium to give high energy power and energy density. This is my material. So first we have synthesized this material as titanium oxide. After that we plan for incorporated with sodium and lithium and potassium. So first my work we have started with potassium. So then we have planned to discuss my work. So next move on to sodium. So this sodium is comparatively give good capacitance compared between the potassium studies. So we choose this sodium. So I means here that is red color dots are the arrangements of sodium, and inside the blue color dots are the titanium. That are alignments between the two like sheet like morphology. While you getting the penetrating of the ions, move on to the in depth of the molecule. So first we have highlights my work. So here my sodium titanium oxide nanosheets for synthesis, simple cost effective method, and then pseudo capacitive nature of explored supercapacitor, and its exhibit a specific capacitance of 670 farad per gram at 1 ampere gram and around 5000 cycle, and made 2 electrode device asymmetric supercapacitor and exhibit 240 farad per gram at 2 ampere per gram around 10,000 cycle, and get good Coulombic efficiency around 97.5 and 87.9 for capacitive tension calculated. So preparation. So here we have take first sodium carbonate as well as the titanium oxide. Both we are mixed with together NXN and directly incorporated with grinding together and with with the use of tubular furnace 960 degree and to get nanosheet. Already we know that is electrode preparation for supercapacitor calculation. So here first we take active material and acetylene carbon and PVDF and NMP with making slurry and coated with the graphite sheet I am using here. People are using nickel foam also. That is a lot of procedure we have, like etching the process is there. But here I am using directly take the graphite carbon and then cleansed with ethanol and directly used for the slurry preparation, and make the electrode for 3 electrode, and then move on to 2 electrode, make a device for the coin cell. So first we have taken physical morphology like physical characterization, XRD studies. Here we confirmed with the 2 peaks of 003 as well as 205 peak of TiO2, and sodium titanate we have incorporated with sodium carbonate in 200 and 201 plane were calculated. And Raman studies 276 and 682 plane were matched with titanium oxides, and 482 688 centimeter inverse stitching the vibration of TiO chain as well as the TiO6 chain. So here morphology confirmed with nanosheets morphology, the same studies as well as the TEM studies. So next we have confirmed with XPS spectroscopy survey spectra. First sodium, that ABC figure are around sodium XP binding energy and Ti2P platform and XPS binding energy of sodium titanate figure. Then electrochemical characterization. So first we have move on cyclic voltammetric studies. In the cyclic voltammetric studies, first we have different scan rates from 5 millivolt to 200 millivolt, and then move on to capacitance derived from the current like CV studies around 180 farad per gram at 1 ampere. So we have calculated from the capacitance derived from CV. And then move on to galvanostatic charge discharge studies, GCD. We have calculated doing like different current density from 1 ampere per gram to 10 ampere per gram. So calculated with A figure, GCD, with capacitance around 680 farad per gram, 1 ampere per gram current density. So after that we have move on to impedance studies. After cycle finishing of 5000 cycles, we have getting Warburg principle of that studies, Nichols plot was calculated. Then we have move on to rate capability studies. Rate capability studies around we have 10 ampere per gram like higher current density put the cycle for 5000 rate capability, and we get 100% Coulombic efficiency. Then capacity retention around 100% and 97.9% around Coulombic efficiency. Then move on to asymmetric supercapacitor. So we take both side current collector. One of my side is material and another side is my active carbon to make a coin cell. And then we have to studies with the uses of battery type material. Then we have to stage for asymmetric supercapacitor device performance. A figure denotes CV, like B figure is the galvanostatic charge discharge studies with take of different current density 2, 4, 6, 8, 10, and then we have calculated with the B figure with current specific capacitance around 245 in the C figure, and then calculated before and after cycle of the impedance studies. This is rate capability studies of the device, my coin cell. So first we have the A figure denotes the capacity, Coulombic efficiency as well as the capacity retention. And then we have calculated the power density and energy density of the figure. So around 6500 power density and 55 watt hour per kilogram energy density we have calculated. Then after finishing my all the studies, in final stage we have all the cycle and capacity retention studies calculated. Then move on to postmortem studies to the material is good condition as well as to do. So we are getting the before morphology studies nanosheets. After my studies will complete also same morphology studies from this figure. So before nanosheets of year, the A figure, and after morphology studies of concluded year. So this is my summary. First, we have synthesized the solid state route, calcium 960 hours, 12 hours for my material. So for this 3 electrode device, we have capacitance around 670 farad per gram, and rate capability studied around 175 farad per gram, and current density is around 10 ampere per gram, around 5000 cycles. They get capacity retention 100% and Coulombic efficiency around 98.5%. Then we move on to the coin cell fabrication of my device studies. In this specific capacitance around 240 farad per gram and current density 2 ampere per gram, and rate capability studied around at current density 10 ampere per gram and stability around 10,000 cycles, and capacity retention 87.9% and Coulombic efficiency 97.5%. And finally we have calculated the power density also, energy density also calculated. And the plan for future work, first now we have in bulk material composites, then move on to design for the supercapacitor device and strategy, and move on to the device like e-mobility vehicles. So energy, it can be seen, smelled or weighed, but it can be produced and stored. Acknowledge it. So thanks to my supervisor, Dr. S. Anandakumar sir. And this is my advisor from Taiwan, Professor Lu. And then my advisor from Mingchi University of Science and Technology, Taiwan, Mani Govindasamy sir. And my collaborator, Uma Maheshwari ma'am, for undergoing this work. And this work is communicated in Chemical Engineering Journal, Elsevier publication. Thank you.
Good presentation, Mr. Shankar Narayanan. Any questions from the participants? There's a question.
Yeah, you have said that asymmetric, so you have said that asymmetric you have done, no? So I hope you did with activated carbon on other side.
Yeah.
So how many voltage you have delivered for the activated carbon?
Actually, that one I'm not putting in this slide. So first we are taking the activity carbon from this around 2 to 3.
You get for activated carbon 2 to 3?
Like, yeah.
Okay. Yeah, fine.
Your synthesis of nanoparticle is by hydrothermal method, right?
Not hydrothermal method.
Which method was there?
We have mechanochemical method, solid state route.
Okay. Is it ball milling is needed before you're going to some or another characteristics?
No, actually, if you're taking material as exfoliate method, like exfoliation we take place means ball milling we are took. But here I'm not taking any exfoliation from this material.
Okay. After when you are adding the reducing agent, that will be needed, I think.
No, actually I'm not here like reducing it. Directly we take the material A plus B, that adding the NX in for mixing property, then we directly took in the tubular furnace and getting the morphology. That's it. If you do mix, that means we can ball milling.
Okay.
Thank you.
Thank you.
This is your PhD work?
Yeah.
Okay, all the best. From my side, I just have a query. You were talking about the lithium, sodium and potassium. You have put for sodium. Did you confirm in the lithium and potassium also?
Yes, sir.
But I can see in some of your slides it was potassium. The diagram, the scheme you have just presented it as potassium titanate. Okay, it's okay. But you have confirmed with others also?
Yes, sir.
So it is all three together you have done the study?
Yes, sir.
So out of that you have selected sodium titanate?
Lithium is better source. We have to
lithium is better source.
Better source.
So that part you are not presenting. Only
sir.
sodium you are presenting. Okay. All the best for your PhD.
Thank you, sir.
Thank you. Next participants get ready. OPESE 26, Harivarshini and P. Lalita.
Very good afternoon to everybody present here. I am Harini Vashni, pursuing PhD in Navinashlingam Institute, and also I work as a project associate in the project funded by Government of India, Ministry of Coal. My research topic is harnessing the electrochemical behavior of bio-derived reduced graphene oxide for high performance supercapacitors. These are my contents. So we all know that carbon is a very predominant element in the world, but the properties of allotropic forms of carbon have been well explored. Its properties like its derivatives like graphene based materials or the existing materials. So graphene is a wonder material, we all know that, and despite of its wonderful properties, it also has some toxic nature, which is very toxic to the environment and also for the health when it is used as the drug delivery, used for the purpose of drug deliveries. And here we propose, we made an attempt to synthesize graphene in a green synthesis, that is by using the plant material as the reducing agent. Hence we undergone a literature survey in which Iconia crassipus is a plant where this is used for the reduction of reduced graphene oxide, and the electrochemical behavior of this reduced graphene oxide, bio-derived reduced graphene oxide, is not studied yet. So the synthesis of this reduced graphene oxide via bioreduction method, here we synthesize graphene oxide from the graphite powder by modified humus method, and then the graphene oxide is taken as a precursor which is reduced by the plant extract in a reflex method. For 6 hours it has been reflected, and then it has been tested and then it is characterized. The reduced graphene oxide is incorporated into the biogenic material, that is the bamboo stick electrodes, which is being used as a working electrode here for the supercapacitor behavior. As in developing countries like in South Africa and in India, in minor places of India, we all have a pressing demand that we all cannot be accessible to the costly electrodes, that is the GC glassy carbon electrodes, which can cost rupees 20,000. That is one electrode can be cost 20,000 rupees, which should be properly maintained, or it cannot be used. The surface of the glassy carbon electrode should be properly used, or else it cannot be used. It will be gone for the single use. So here we made an attempt to synthesize the materials and incorporate into the plant material bamboo, where we stuffed the modified carbon paste, and then we made a slurry, and then we incorporated this RGO as the surface material. So this RGO is characterized by UV, where the dark brown color solution of graphene oxide was changed to the black color solution, which shows the spectra of 234 nanometer to 296, and then the comparison of FTIR spectrum shows the effective reduction of GO graphene oxide. So there you can see that the oxygen functional groups are being reduced, and some more even disappeared, and the XRD pattern of GO and RGO, there is a shift from 10 degree to 26 degree, and the restacking of the graphene oxide has been reduced, and the FESM images shows that it is of sheet-like morphology, which will be apt for the energy storage applications. And the electrochemical behavior of this reduced graphene oxide, which is incorporated in that electrode, bamboo stick electrode, which shows that is the blank, first one is the blank carbon paste electrode, which shows the CV graph of that, in which we can visually see the potential range is very less, and when compared to the RGO incorporated one, it shows a maximum specific capacitance value of 99.6 Fg inverse. And this is the charge discharge curve, where this active sites of the RGO has been allows the electrode to interact, that is the electrode and the electrolyte surface interface were very good, and hence we got this capacitance, higher capacitance. So the practical application, here we have incorporated the RGO incorporated electrodes and we ran a CPU fan with a DC voltage, and it is kept as the electrode has kept as the positive terminal, and here we have observed the minimal voltage drop, and it has been run for 10 minutes, and there is no leaching out of samples, and also for 10th use also the repetitive measurements were got, which shows the reproducibility of the electrode. So in summary, to reduce the environmental impact of the graphene, we opted the sustainable method of preparation, and also the characterization shows the effective reduction of graphene oxide, and this suits for energy storage applications, and for the improvement of conductivity, we have developed a prototype, and which showed a high performance of 99.6 Fg inverse. So these are my references, and I acknowledge Bharat Ratna Professor CNRO Research Center for all the facilities, equipmental facilities, and I acknowledge the project funded by Ministry of Coal, Government of India, for the financial assistance. So I here address the global goals, the sustainability goals of affordable and clean energy and sustainable cities and communities. Our research objectives not only serves the scientific communities but also for the local communities. Thank you.
Thank you. That was a nice presentation. Any queries from the audience?
And we wait for some time for coating and all. So how about the absorption rate and all for the electrode you prepared it?
Actually for GCE we will be using that drop casting method, the one for sensing applications. But here we use for energy storage applications that we test for the conductivity alone. And here we have, after the synthesis, we will be drying the material at hotter oven at 100 degrees Celsius, about that. And the surface will be cleaned.
No contamination interferences and all? Contamination interferences?
As of now, we have tested the conductivity alone. There is no signal to noise ratio and all when we tested here. But we will be taking for the application of sensing. At that time, we'll...
Okay. Only one question, another. The bare thing have you done?
Yes, blank thing we have done.
Bare working electrode you have done?
Yes.
Bare thing. So you have got pseudo capacitance or normal thing?
We have got pseudo capacitance, as you observe this.
Blank also you have got?
No, for blank we have, we didn't get the pseudo capacitance or the EDLC behavior. There is nothing, a very minimal voltage of 0.0001 voltage.
No redox peak and all was there?
Peaks.
Oh, good, thank you.
Any other queries from the participants?
Yes, sir, one more question. Ma'am, your presentation is very nice. I would like to ask you one question.
Thank you.
Can you please go for your GCD graph?
Excuse me?
Excuse me, can you please go for GCD graph?
Slide.
Do you have any idea something is wrong in it?
Yes.
Yeah, what is that?
There is an increase in potential also.
Yes, of course. Why?
I don't know, but when we increase the this current density values.
No issues, I will let you know. The open circuit potential of the each cycle is little bit increased. Okay, because that if you are considering the 1 ampere per gram, it's the black line. Then you are considering the, if you are increasing the current density, the open circuit voltage is also little bit increased. This might be due to you are not stabilized your electrolyte. So how many cycle you have previously, how many cycle you want to run to stabilize the electrolyte? May I know which molarity of your you are using electrolyte, whether it's acid based or
alkaline based, 3 mKOH.
3M?
KOH.
Why you are going for 3M? Why not for 6, 9, 12?
As we use this 3 electrode system, we are using this AgCl electrode. So hence it will be gets damaged when we go for higher percentage of this concentration.
No.
So hence
I'll let you know. Like if you are using the AgCl as your reference electrode, you can go up to 0.6 volt. Instead of you can use mercurous oxide, you can go up to 1.2 volt.
Yes.
Then one more thing is, I have some little bit doubt in your CV graph. This blank CV, you doesn't get any kind
redox
of
peaks.
Not redox peak as well as the supercapacitor nature.
Yes.
Why? This is not a rectangular.
Yes, because it is just for the carbon paste. There will be we have put silicon oil also for the construction of that. That may not be conductive.
Then at the same time, in your next graph, you are using some. You got get some one oxidation and reduction.
That is of this reduced graphene oxide material we have incorporated in the surface. So that surface, electrode and electrolyte surface, there will be no. So
may I know what is mean by CP? Carbon paste, right?
Yes, carbon paste.
There is no metal oxide is there in it?
No.
Okay, you can just recheck that. If there is no metal oxide means there is no reduction peaks.
Yes.
You can just then one more suggestion, if you are using the current density.
But for RGO we have done blank.
Okay.
Using nickel foam electrodes
Some
and all
impurities is might be there.
No, for that there is oxidation and reduction both.
You are using potassium permanganate for your Hammers method, right?
Yes.
Then you are using hydrogen hydride, right?
No,
for reducing.
no, we didn't use
Then
hydrogen hydride.
Okay, then sodium?
We use only the bio-reducing agents, that is the plant. Yes.
Okay. Then one suggestion is, if you are using the current density in your y-axis, you don't write this much of decimals.
Yes.
Yeah.
But we have got...
I understand your point.
Yeah.
Thank you so much. Nice
Yes,
presentation.
Thank you.
Can I ask you only one last question? They have enough drilled you. This last question is, you have used a bamboo stick electrode,
Yes,
right?
sir.
What is the practical difficulty in using this bamboo stick electrode? Are you comfortable with using that?
Sir,
Why you have chosen that? Because of cost effective?
Yes, sir. We have GCA electrodes, sir, but it is a bamboo is a porous material, and if we go for this like low cost electrode, it is what to say, sir, it is a cost effective one, and also incorporating this plant material will be an innovative one for the electrochemical
so because
studies.
of innovation and cost effective, you have chosen
Yes,
the bamboo stick. Okay. Thank you. All the best.
Yes, thank you, sir.
What is the funding? How much funding you got for this project?
So this is not a project of what I told. That is another project. This is my research work.
Okay. Okay. This is your PhD work.
Yes, sir.
Okay. Okay. Fine. All the best.
Thank you, sir.
Thank you for your presentation. And now it's time for a tea break. I request all the attendees to back within 5 minutes. Shai Shakti, Miss M. Ramya. The presenter are requested to complete present within 3 to 5 minutes. Next participants OPE AC 36 Kanimoli, Kannabiran. Get ready.
presenter till they get ready.
They are waiting for PPT, sir.
Okay, okay.
Chandrasekhar. Age 36.
Good evening to all. I am T. Jayavatni, coming from NPR College of Engineering and Technology. We are presented by fabrication of smart, wearable and triboelectric generator and development intelligent and rudimentary system or genetics. Next slide. Introduction. The recent years of wearable health monitoring device, which is significant and attachment due to the potential and personnel of the healthcare. This device issues visible signals like that heart rate and physical activity when stress levels, when help detected to the easily signals is medical is conditions. The various technology is the triboelectric nano generator. It is shown in for the energy efficient of the self power of the solutions. The tribo nano generator we are device which is converted into the mechanical energy such as body movement and environmental movement. Triboelectric efficient generator is the change is here two material into of this connect and separate. This technology is a small scale power generations. The key enable of the self power of the sensors. Wearable of the healthcare this device. The health monitoring sensors without need for the external battery and wired connections. Materials and methods. Materials and methods. Materials. Tribo nano generator is material therefore classified as a two type. Electrode materials and triboelectric layers. Wearable and substance materials therefore classified as two types. Flexible substance and textilent based on substance. In eco solution and materials, power management and components. Methods of fabrication of the TENG of device. This classified as the three types. Layer depletion, electrode depletions and assemble. The device or integration into variable platform. The categorization and testing, output, performance and testing is in this sensitivity and testing.
Good evening to all. I am tell about the topic of the result and discussions. First, it is a monitoring systems on the SWS. It is O in the shoes. On the right, elegate in the system SWS. It is have a side channel on the acritic cell on the ion rotating and the formed on the acritic cell. The working principle of the side channel is based on the coupling effect. Triboelectric and electric inductions have a dielectric layer. It is in PTFE film produce uneven charge distributions resulting the transfer of the electrons. Between the uneven charge distributions, the resulting transformer of electrons between the two electrodes balance level local potential distributions. It is ore in the shoes. SW is in the ore in the shoes. It is use of healthcare monitoring. The portion of D is voltage distributions between ion ball and PTFE film with along the circumference, and the CF of the diagram is the voltage distribution between the ion ball and the PTFE film with the ion jumping down, up and down. It is due to the convenient and comfortable wearability of the SWS placed on the different part in the human body. The amplitude of the recent time under the each motion state were different. It is alarm on the fall down and sleep monitoring to demonstrate the SWS can serve as sensing device for actual sensor real-time health monitoring system has invented. To demonstrate the SWS can serve as a sensing device for the actual sensors. The system consists MCU, Bluetooth transmitter, Bluetooth receiver and underlay software which is exposed. It is also placed on the neck monitor to the sleep state in actual time. When the user lay flat on the bed and breathes normally, an amplitude was small, response time was long. The summary of this topic is wearable and practical small sensor based on the two-channel is demonstrated for true time health monitoring. It is have low cost, convenient wearability, high durability, short response time and excellent water resistant. This research process new design scheme for wearable motions monitoring and equipment. Thank you. Thank you, sir.
The topic is open for discussion. Any queries from the participants? Which year, ma, you are? Which year and which department?
Final year.
Final year, engineering. Which department?
Triple
Triple E, okay. Any queries from the participants? So this is an ideation or you have developed the sensor?
No, sir.
This is just you are giving an idea, like this
yes,
we can develop.
Yes,
so this is just an ideation,
yes,
that's all.
Yes, sir.
It's not done. Okay, thank you.
Thank you, sir. Next participants OPEAC 36, Kanimori Kannabiran. Next participants get ready. OPEAC 38, B. Purushotman Reddy and M. Chandrasekhar.
Good afternoon to one and all present here. My name is Keethika. We are coming from NPR College of Engineering and Technology and we are final year Triple E. Our topic is about harnessing energy from low frequency and low amplitude vibration sources using triboelectric nano generators. Vibrational energy can be done using a triboelectric nano generator with low frequency and low amplitude. In today's energy world, they're harnessing energy from low amplitude and low frequency sources such as in human motion and wind energy and wave energy. Here we are the contents of about our project. And triboelectric nano generators are devices that can convert mechanical energy into electrical energy through triboelectric effect and electromechanical conversion. This energy conversion techniques includes with mechanical energy into electrical energy. And by triboelectric effect, when two materials includes when polydimethyl silicon with aluminum foil, it will be sandwiched together, and in between that there will be an electrodes, and this electrodes transfers charge to one place to another, And in electrostatic induction, the materials will be separated, and it improves the electrical field and produces current and generates electricity. And this trielectric nanogenerators are unique to harness energy from low frequency and low amplitude sources. And here the materials includes in triboelectric nanogenerators. Triboelectric nanogenerator materials includes polyvinyl dilyl fluoride and polytetrafluoroethylene, and polydimethyl silicyoxane is the primary source in triboelectric materials. And inorganic materials includes in electrodes, zinc oxide, silicon based materials and aluminum, etc. And polymer dielectrics includes polymethyl methyl citrate and silicon elastometers and ceramic materials. And the methods includes in triboelectric nanogenerators. We can use alternative methods using stress strain method, and for low frequency to high frequency improving methods. And here the energy conversion principle improves energy density and electromagnetic principle. It is the main purpose to convert mechanical energy into electrical energy. These steps includes first this triboelectric nanogenerator will be at the capacitance will be at minimum stage. Then the force will there will be a mechanical force, and then the capacitance will be at maximum level, and remove the mechanical force. It will give an thickness and decrease to electrode area, and the electrical energy will be produced by the nano generator. And this is the parameters includes in triboelectric nano generator. It includes hysteresis laws which will be created in nano generator. In triboelectric nano generator, it will be in maximum at range and minimum range. And my friend will continue the next.
As my teammate have introduced in the before, we are using this technology triboelectric nanogenerator in the wind energy, human monitoring, human motion and wave energy. As from the wind energy, in the normal electrical science we can see that when the wind blade rotates, we can generate energy on a low motion with a minimum voltage and current. But by using this technology, we can improve the low optimization into a little bit of high voltage. As you can see here, the approximate output and average peak power 10 megawatt, we can increase that by the speed of 2 to 5 M/s. 2 to M/s. And we can use this. We can also know that an windmill will run in a low speed. So using that low speed, we can generate electricity with a engine, with a generator. And also using this triboelectric generator, we can also generate electricity. Human motion by fixing a cello tape like with this device, we can generate electricity from normal human movements. And we can also generate wave energy in an electrical and electrical. And wind energy is a renewable energy. We can also generate this electricity by using this technology. So summary and conclusion. As we have concluded that it is a sustainable and renewable energy, it can be wearable. From the starting we have said a human can wear, and human can generate electricity in a low optimization, and it can also be in the future it can be turned into smart cities and renewable systems. It can be used in the self-powered sensors, and it is a low consumption device which can produce energy, and energy generation in low marine environment also possible, like in wave generations. And these are the references we have taken from. And thank you, sir.
Thank you for the presentation. It's open for discussion.
Thank you, sir.
Thank
Next,
you.
who is, anybody is willing to present a paper except these? Okay. Now I invite OPESC 50, Sivagami.
Yes, that is your next. A very good afternoon to everyone. So the topic of my presentation is advanced application of highly stable boron nitride nanotubes, and also I will be basically talking about the assessment towards the industrial scale production as well as about the sustainable future perspectives. So my research group included me, Mr. Vivek Yadav, Professor Vinayaka, Professor Omkar Singh Kushwaha and Professor Tejraj M. Aminabavi. So with them this has been a 4-year research work which has been developed into different stages, and this is one of the stages that I'm going to be talking about in this presentation. So first of all I will be talking about the contents. So first I will be introducing what BNNTs are, and then why we should be choosing BNNTs over CNTs, and the advanced application of BNNTs, then the methodology, and then the FEA analysis, that is going to be the main part of the presentation, and then how we are going to be industrially scaling up the production and the synthesis processes of BNNTs, and then the market and techno-economic analysis of BNNTs, and then concluding and references and acknowledgement. So first of all, what actually is BNNTs? So imagine you have a carbon nanotube, okay? So there is a carbon nanotube, there are a lot of molecules of carbon attached to the full nanotube. If you replace all the carbon molecules and you attach alternatingly the boron and the nitride complexes, which has been bonded as shown in the figure, then you are going to be getting a complex which is known as the boron nitride nanotubes, okay? So why actually we are using boron nitride nanotubes and not carbon nanotubes, and what actually is important here? So the main thing is it has very high thermomechanical stability. Other than that, it also has very high tensile strength. These are the good parts about the BNNTs. Now what is the limitation of BNNTs? It is that it has a very low yielding synthesis methods. It has very less efficient synthesis methods that makes the cost to increase it. Okay, so that is what I'm going to be talking in the presentation about, how we can lower the cost, how we can actually shift the better synthesis methods for BNNTs, and how we can actually have a new advancement in the nanotechnological world and the research world. So moving forward is why BNNTs over CNTs, and is it the present or the future of nanotechnological advances? So I'm going to be talking about the properties of BNNTs over CNTs, okay? So as you can see in this particular figure, so there is a huge band gap as we see in the boron nitride nanotubes, which actually shows that in a lot of thermo insulation applications and everything, BNNTs would be preferred over CNTs. The Young's modulus is also, which actually talks about the deformation capacities, which talks about the mechanical capacities. It is also somewhat equal to the CNTs. And now after that, if we are talking about the thermochemical stability, it is much higher than when we are talking about the CNTs. And finally the optical properties, in which it has a deep UV regime, whereas CNTs only have a near IR regime.
So moving forward are the advanced application of BNNTs. Now all the applications that I have particularly shown here are something which has not been proposed before. This is something which I am from our own research work, from everything that we have discussed, we have actually proposed some of them. So first of all, if you can see the first figure there, it talks about the sensing applications, especially in the humidity sensors. So in that case, BNNTs can be used. The second part is for the bulletproof vest. So if we can have a layer of BNNT which is actually going to lower the cost of BNNT and the bulletproof vest, it actually is very helpful due to its mechanical properties, that it can also be used as an alternating of Kevlar and all those things for BNNT. The third one are for the biomedical applications, in which in the drug delivery, gene delivery, etc. it could be used. And then the major part of my research work, which actually talks about the hydrogen storage. So actually BNNTs could be used as a layer for the hydrogen storage applications, and through that layer is something what I have done in my research work, which I am going to be showing in the next slides. So moving on is that, first of all, there has been a lot of presentations I have seen right now today. They are all talking about characterization stuff and everything. But what I have done here is, rather than talking about the lab scale research, I have taken it one step extra, because last year when I came to iNEEBA, I also gave the lab scale research and everything. This time what I particularly talked about is the industrial scale part. Now how are we going to be industrially scaling up the hydrogen storage facilities through BNNTs? So what we have personally done is, we have formulated a new model, which is the input-output model. So as the name suggests, what I have developed in this model is that we have to give some input parameters, and through the input parameters there are some intermediate formulas which has been given here, which calculates the mechanical strengths of the BNNT material, and through that we are getting a lot of output values which showcases what is the mechanical strength of BNNTs, and that is something that we have done. Now what are the input parameters that I have mentioned in the pink color flow chart that you can see here? So there is a material selection that we have to do, in which it is obviously BNNT, and then going towards the mean and the ultimate tensile strength, then the compressive tensile strength, the stress, temperature and pressure. So finite element analysis, what it actually does is, it tells whether the object and material, how it is going to be reacting at different operating conditions, and that is something what my research work has shown. So this is basically a 2000 liter capacity hydrogen storage setup that we have virtually simulated in the trying to make it as similar as the actual real world. And when we have put on all the atmospheric pressure conditions, when we have put on the temperature which is necessary for both hydrogen as well as for the BNNT surviving, this is what the results that we got. So first of all, when I'm talking about the total deformation results, so as you can see on the results are actually showing about the maximum and the average values of total deformation, and it is also going on for the other results and discussion. So what does this actually mean? So this actually means is that when we are talking about the simulations and the computational aspects, it only gives one value, okay? So what we does is, we give it in a range format in which there is a minimum value for the minimum operating conditions and then the maximum value, and then we are taking the average of it and then it is showcased. So what does this finite element analysis signifies when we are talking about this particular thing is that the BNNT layer, which is on the interior part in which the hydrogen is actually getting stored, it is absorbing all the hydrogen deformation which is caused by the hydrogen in the storage, and it is not letting the exterior material to cause any harm. It was a 1-year simulation that was done by us, and it actually showcases that there is not much deformation when we are talking about the exterior part. Now same goes for the equivalent stress that we have shown. Hydrogen is known for giving a lot of equivalent stresses to the material, be it structural steel, be it CNTs and all those things. So what this result actually showcases is that all the equivalent stress which is pushed by the hydrogen towards the material, with the interior material where it is getting stored, BNNT is able to actually capture all that stress and not letting the outer material to get through it. Now, when I'm talking about the strain energy, this is the most important aspect of our research work. So as you can closely see that through the color coding scheme of the FE analysis, you can see that there is no red color pressure points much in the strain energy. What does this actually signify? So it actually signifies that when the strain energy is getting absorbed by the BNNT material, it is getting stored. Not only the hydrogen is getting stored, but also the strain energy is getting also consumed by the BNNT, not letting the exterior part. So what is the significance of this? This is going to be the next stage of my research, in which we are going to be actually trying to convert that strain energy into some sort of a consumable energy, so that when we are talking about the hydrogen storage aspects, it is also able to store energy as such other than the hydrogen storage aspects. And similarly, it goes for the equivalent stresses as well as shown in the figure. Now it shows the industrial scale up of BNNTs. So this is actually something that has also been accepted as a patent also from our research group, and this is something I'm going to signify. So now we are talking about the industrial scale up of BNNTs. So there are a lot of synthesis methods, and a lot of synthesis method which other researchers have also done, they have not shown a good yield of BNNTs. So how are we going to do it? So basically there are two major methods through which BNNTs are produced. The one is a substitution method and the other one is the CVD, the chemical vapor deposition. So basically when we are talking about this, so the boron oxide cylinders and the nitrogen generators, they combine together in order to form BNNT. But at the same point in the substitution method, the major byproduct is carbon monoxide, which is also a pollutant. So how are we going to utilize that? So as you can see, the carbon monoxide storage tank, it actually also combines with the hydrogen which has been produced, and through the distillation of syngas, we are able to also generate electricity. So that electricity is also used in the chemical vapor deposition in order to produce BNNT again, making it a very circular form of industrial process optimization. And that is something that has been shown. And also on the top, as you can see, when we were also doing the cost benefit analysis and the techno-economic analysis, there was also the revenue generation model which was given here, and it actually showcases that after the running of 10 years of the industry, through this particular optimization, the industry is actually going to gain profit. It is actually going to give consumers electricity at a lower cost, as well as the cost of BNNT is going to decrease. The actual cost which is running right now is 2500 per gram for 100% BNNTs. And through this, it is actually going to decrease to 250 rupees per gram. And as we are going to move forward with the research, it is also going to decrease as we go on. So moving on with the market and the techno-economic analysis of BNNTs. So first of all, I have mentioned our market size outlook, in which with the help of previous data and through the compound annual growth rate data, we were able to project it. But what is the credibility of it? Like, it is currently also increasing, that is true. But through the industrial scale optimization and through the tech transfer negotiations that our research group is also going, if everything succeeds, this is going to actually grow exponentially, and something which is going to be differ from what I have shown in this particular graph which has been mentioned here. That's why in the lower graphs I have actually shown in the percentage values, because even though the exponential increase will be there, the percentage of the application variability and the differentiation will always remain the same, and that is something that I have shown here. As I've also concluded the points in between the slides, I'll still give a small summary, in which actually the yield of BNNTs, it could be increased through the modified substitution CVD method, which I have shown in the industrial scale up. At the same time, the FEA of BNNTs actually showcase a better result than CNTs and structural steel for hydrogen storage and other high pressure energy gas storage if it is run for 1 year to 5 years. And at the last, I also want to say that the mass production of BNNT should not be reduced because of the conventional mindset of researchers, especially international researchers and everything, because we have the power to substitute carbon nanotubes, which are also unsustainable for the environment. We have everything, and we are also working on it, and I hope that also the future researchers and everyone sitting here also give a thought of it, and we can also collectively start and working towards the next advancement of nanotechnology. Lastly, I would like to mention all the references. Some of the papers have also been published through our research group and some other ones, and also the acknowledgement to everyone who has supported me in this full research journey. And I would also like to say that my first presentation ever was 4 years ago, in which I presented on BNNTs, and this is the third time I'm actually presenting on BNNTs, and probably a lot has changed in the middle, and I would like to thank everyone. Thank you so much.
Thank you. That was a good presentation, and you are confident enough to showcase your presentation. Any queries from the audience?
Good evening. You have done a very nice presentation. Actually, one thing I would like to appreciate you is you are scaling up the lab scale to the industrial level. That is quite interesting.
Sir, can you please be a little louder, sir?
Yeah, sure. Then one more thing is, I have a small suggestion and doubt. You are telling about the hydrogen storage, right? I have one basic questions in hydrogen storage.
Yes.
May I know the purity of the hydrogen storage and how you are stored, and what about the Pascal of the storage?
Yeah. So first of all, the purity of hydrogen. Yeah. So actually, I have one of my startups also running through it, which also works on the hydrogen storage.
No, I can't understand.
Yeah. So the two purities that we have worked on. One is with the ammonia. Okay, so the purity is 60% hydrogen, and that has been produced by the ammonia. And the second one is actually from the hydrogen-nitrogen complex, because nitrogen is the inert one. That is 70% hydrogen and 30% nitrogen. And now we are talking about the pascals. So when we are talking about the industrial scale, we are actually talking somewhere around the lines of 40 to 50 bar. And in this particular research, I have taken 45 bars.
You are storing the hydrogen is like a liquid form.
As a gas.
As a gas.
Yeah.
Okay. Then one more thing is you as the end of your conclusion you said this is the second time you are presenting boron nitrate nanotubes. Right? You have any idea about the borofin instead of boron nitrate? You have done so many simulation. If you are using borofin, you have any idea about instead of boron nitrate nanotubes?
I'll be honest about borofins. I've read in the literature, but I have not worked with my research group on that. So definitely I'm going to go back and I'm going to definitely research about it.
Because boron nitrate nanotube is having the small conductive material compared than the carbon. So right now so many research is going on for borofin. So it is super material which is compared to the graphene or carbon nanotube or somewhat.
Actually, while you were asking this question, I also got an idea in which what about there could be a complex about either boron nitride and borofins or even boron nitride and carbon nanotubes in order to increase the efficiency.
Yes.
And that is something that we can actually do.
Yes, correct. Yeah. Best wishes.
Yes. Thank you so much.
Thank you so much.
Yes.
Any other queries? So you are a PhD scholar?
Yes, sir. And
have you submitted your synopsis?
No, sir. It's my first year.
You are now in first year of your PhD.
Yes, sir.
But you told you have done all this works 4 years before.
Yeah, sir.
So your PG project.
I started my research when I was 16 years old, sir. I just
16 years old.
And my first research publication was when I was 18 years old. So I
congrats.
started doing that.
We can see the confidence in you during your presentation.
Thank you so much, sir.
Best wishes. Do you have any industrial collaboration for this?
Yeah, sir. Actually, with my startup, we are collaborating with Shell.
You had your own startup?
I have my own startup running also, sir.
You have your own startup running also?
Yes, sir.
What is your age now?
Sir, right now I'm 21.
Please give him a big clap.
Yes. Thank you, sir.
Best wishes.
Thank you so much.
All the best.
Thank you so much.
Wish you good luck for you. Next participant, OPEAC 50, Sivagama Sundari. Next participant, get ready. OPEAC 40, Moses. Get ready.
So good evening, everyone. So this is the same topic as both of some people have took upon supercapacitors. So I'm Dr. Shivagami from Crescent Institute of Science and Technology. So this is my title, Electrochemical Performance and Functional Characteristics of Nickel Incorporated Cobalt Molybdate for both supercapacities and lithium-ion battery applications. So this is just an introduction as all you have said. So it is just the need for energy storage device, the growing population, depletion of fossil fuels and trend of portable devices. These are something common. So this is just an introductory slide for what is energy storage devices. And this is what, so I basically work on electrochemical energy storage, basically on supercapacitors and batteries rather than fuel cells. So these are the various applications of electrochemical energy storage devices. So this is the introductory slide for batteries. So this is just, and this is the fundamental things about the primary and secondary batteries. So these are some applications and all. So as some of you said about the supercapacities, these are some of the introductory slide and classifications of supercapacitors, AA capacitors, pseudocapacitors and hybrid capacitors. Here high This paper projects on pseudocapacitors, basically battery type electrodes were used. Okay, these is also some of the introductory things as you all said. So I move on to my synthesis and electrochemical characterization. So this is the basic synthesis. My novelty work is not on the material side, but on the electrochemical studies and prototype fabrications and all. So this is the normal hydrothermal synthesis I have done with different nickel ratios of nickel into the cobalt molybdate. I have missed annealing actually, so that is one part I have read it out. And so coming to the electrochemical studies, here I have did for both the 2 electrodes and 3 electrode study. So this is what, so I have synthesis nickel molybdate, cobalt molybdate and nickel cobalt molybdate. I impregnated different percentages of nickel into cobalt molybdate. This is the basic thing. So this is the CV profile for all the 3 synthesis material at 20 millijoule per second. So the working electrode I used was nickel foam as the working electrode, and this is the GCD profile for all the 3. Basically the nickel cobalt here I have done is 0.5% of nickel into cobalt at 5 ampere per gram for galvanostatic charge discharge study. This is the basic primary study of this. So coming to this, as the electrode preparation, I have used 85% of the active material like synthesized nickel cobalt molybdate. I also used the nickel molybdate, individual molybdates, nickel molybdates and cobalt molybdates also. 85%, 10% carbon PVDF and 5% of PVDF, 10% of conducting carbon. And first one is the CV profile of cobalt molybdate with different percentage of nickel into the cobalt molybdate. So here you see the black thing is the nickel cobalt molybdate with which has 0.5% of nickel. So here the current is also increased here. So and, the next slide is about the nickel cobalt molybdate at different scan rates 10 to 100 millivolt. As we all know, as the scan rate increases, the current also increases. So it has also been proved here. So coming to the next one. So here the galvanostatic charge discharge of the cobalt molybdate with different percentages of nickel have been done. So here you see the cobalt molybdate has higher discharge time compared to that, but the nature of the curve that is obtained is a correct way of the GCD profile. So this is one thing I have absorbed here. So coming to the part of 0.5% of nickel and cobalt here, this is the different GCD profile ranging from 1 ampere per gram to 10 ampere per gram. So from this CV, I have got the specific capacitance of around 450 Faraday per gram at 1 ampere per gram current density. So coming to the EAS part, so this is the EAS profile of cobalt molybdate and nickel molybdate. So here I have just said about the solution resistance. So the solution resistance of the nickel cobalt molybdate is lesser than the cobalt molybdate. So once the resistance is lesser, the conductivity becomes higher, the ionic transportations will be higher and the kinetics obviously will be higher. So this is one of which it represents the good stability of the material. So this is again the cyclic voltammeter with different current density. As I said, different percentage of nickel was impregnated to the cobalt, and it is just the different scan rates of what it is done. So compared to all the nickel which I have incorporated, 0.1, 0.3 and 0.5, 0.5 has this more stability compared to the other rest of the things. So it is just proved it. So here I have got these, this is from the CV graph that I have got the area, combined area of the integral area of the CV here. So this is what. So again the different current densities were subjected to all the 3 percentages of nickel incorporation, and this is what we got it. And the same thing, and here the last one is about the nickel cobalt molybdate at 0.5 and 0.5. So we have got around 592.5 Faraday per gram at 1 ampere per gram. So these are the studies which I have done. Okay, then comparing the EIS of all the, first thing was about all the nickel cobalt molybdenate thing. Here specifically on nickel impregnate cobalt molybdenate. So this is what, and the nickel cobalt molybdenate has the least solution resistance here. So again, here what I have did is, flexible thing I have tried it with the graphite composite flexible substrate, and I have also done with the bending cycles. So almost 100 cycles have been done, and the cyclic voltammetric technique was done, and there was no significant difference in the CV here. The same capacitance almost was got. That's all about the 3 electrode. Coming to the 2 electrode, I did with coin cell. So here, the first thing is about the cobalt molybdenate and nickel molybdenate, 0.5%. I have got around 1.8 volt. Here, the activated carbon part I have also not shown here. The second graph is about different scan rate for the nickel cobalt molybdenate at 0.5%. So here I have got around 600 Faraday per gram at 1 ampere per gram current density. So the third graph is about all the current densities of the nickel cobalt molybdenate. These are on all the electrolyte is 6 molar kWh. The fourth graph is about the electrolyte is organic liquid. So hence when the potential is increased, so all the other potentials are around 1.6, 1.8, but the potential here increases to around 2.5. This is because of the electrolyte. And about the charge discharge cycles, cycling cycles. So I have got around 600 Faraday per gram for the 2 electrode of KOH, organic liquid, and for 200 Faraday per gram for aqueous electrolyte. This is what. So here I said this is about the supercapacitor application. Coming to the lithium ion application, the part 0.5%, nickel cobalt has been selected as the proficient candidate for lithium storage battery application. So here the active material, so the thing is dual property. So the same material has been used as the cathode material for supercapacitors and anode material for this lithium ion battery system. So here the first thing is about, these are the 5 cycles I have shown you here. It is in 0.1 C rate. So here the first cycle you see there is 3 reduction peak down. So the redox peak down is due to the formation of SEA formation. So when you see the second, fourth and fifth, they do not have that peak. So this confirms that there is something happening in the first cycle. So that is what the SEA formation in the battery discharge cycle. So this is the graph for the 0.1 C rate. This is the dQ by dV graph. The second graph is the charge discharge cycle. Here I have given you all the 0.1 C rate. So first and second, third cycle. So discharge capacity is found to be around 1300 milliamp hour per gram. And charge capacity is seen by 1100 milliamp hour per gram. So there is no much difference in the charge and discharge capacity. So this is also due to the formation of the SEA layer. So there is something happening in the SEA layer, like there is formation of the SEA layer. So the charge and discharge rate has not been very different. So this also confirms the stability of the material what we use. Okay, coming to the third thing, the same charge discharge profile at 1 C rate. So here also we have got the discharge capacity of around 1000, charge capacity of around 900 milliamp per gram. So this also confirms that for 0.1 C rate we are getting 1200 almost, and in 1 C rate itself we are getting 900. That also confirms the stability of the nickel cobalt molybdenate. And this is the cycling performance. So initially I have done for 100 cycles. For 50 cycles the capacity loss has been found, and this is also due to the formation of the SEI, and the stability has been done after the 50 cycles. So we have got around 99.9% of Coulombic efficiency for this. The energy density I've got around 1000 watt per kg for the second and third cycle at 0.1 C rate, and this is for 1 C rate I've got 900 watt per kilogram. So this is all about the lithium ion storage. So conclusion is that both the materials have been, the same material have been used for both the applications, for supercapacitors and for batteries. So this is the hydrothermal approach I've got. For supercapacitors I've got around 300 Faraday per gram at 1 ampere per gram for 3 electrode. For 2 electrode around 60 Faraday per gram at 1 ampere per gram. For lithium ion battery I've got around 1000 for first cycle and for 900 at 1 C rate, the same 900. So thus it demonstrates the same material can be used as the anode and the cathode for both the energy storage system. Thank you. Any questions?
Any questions from the audience?
Ma'am, very nice presentation. I would like to ask you some few doubts. Can you please go for that impedance spectroscopy? Impedance spectroscopy. Slide. This one as well as the previous one, you can check the x and y axis values. Whenever you are plotting the EIS, you can choose the x and y axis values as the same. Then only you can able to understand whether the semicircle or disordered semicircle or is like a Warburg region or somewhat. Then one more thing is y axis you are using minus. Then one more basic question I would like to ask you is nowadays the people are working cobalt free materials, but in your cathode material you are using cobalt. Do you have any clarification about it?
For supercapacitors or batteries?
Yeah, yes.
For both the things?
Yeah, yes. Because the rate of the cobalt is really very high. There is no mining to get much of cobalt right now.
Yeah, for that only we are incorporating some of the nickel into cobalt,
Cheapest
the same
material.
Percentage, yeah.
Cheapest material you are using to incorporate the cobalt.
Yes.
Okay. Then the application is okay, nice.
Hi, nice presentation. Can we go for the impedance spectroscopy? This one. Here you have mentioned that you got high capacitance and high electrical conductivity. But in your impedance spectroscopy, the circuit diagram shows 2 resistance and 1 capacitance. How you can explain that it has higher capacitance than the higher resistance?
Okay. So first thing is that I have seen only the solution resistance I have told you. Okay. For supercapacitors, we also want to see what the Warburg resistance is. Compared to battery, we have to see that. Here, only I have seen the solution resistance, but also I didn't insert the picture here actually. So I have inserted the zoomed picture from 0 to maybe 1.5. From there I have calculated the RCT actually. So it is not visible here, but I have done for the RCT here. But generally I use it for just RS. I have been stopped with RS to just see what is the conductivity of the material depending upon the RS value.
Okay. Then your battery materials CV. Before this. Here you have higher reduction than the oxidation. Why?
Okay. Here the thing is, this is the primary data where I have optimized the activated carbon. So I have derived activated carbon from waste shells. So here the thing is, the nickel cobalt molybdenate didn't show the correct redox peak. So there is a hump, not literally, there will not be a more specific redox peak, like more peak, there will not be there. So only there is a, here I try to justify it in terms of the integral areas of the CV.
Okay, but somehow you have to justify this, no? Because you are using cobalt, nickel and molybdenum.
Yes,
that.
yes. It's just a primary study, just I am justifying here into the integral areas as we get the specific capacitance from that. But I do on the different percentage also, and will do the synthesis as you said. It's just a preliminary study of the 2 electrode actually.
Okay. All the best.
Thank you.
Any other queries? So we can call for the next presenters. Last, my one query, what made you to combine this cobalt and nickel? What instincted you to combine this cobalt?
Actually, I was working on nickel oxide. Generally, I was working on nickel oxide for supercapacitors. I just was working with that, and I had an idea of putting the cobalt together for the supercapacitor application, but it didn't work out. I did with different ways of methodology, but I just wanted to do it hydrothermal synthesis. I just wanted to add different percentage into it and check for it. Once I got some primary result, this is also a primary result. Before that, I had some of the primary result also that showed higher capacitance till 1000 Faraday, 1200 Faraday per gram. Then I had an idea how I can incorporate nickel into it. So
okay, thank you.
Thank you.
Thank you, sir. Next participant, OPEAC 40, Mr. Moses.
Good evening to all. I am really happy to present some part of the research work, ongoing research work. I basically work DJ Sangvi College of Engineering, Mumbai. I'll be presenting part of simulation work. Okay, altogether it's simulation work on diffusion limited aggregation of polymers with anisotropic interactions and some signatures of phase transition which I got. So I basically work on surface growth model. Suppose if you have systems which are going from the surface, thin films or molecules or colloidal systems which are aggregating in the solution. So how we can able to simulate such process. So there are different growth models which researchers used to use. For example, there are ballistic deposition growth models, Edward Wilkinson model, etc. But in this work, I will be in this presentation, I will be restricting on diffusion limited growth model, which is basically used for aggregation of colloidal systems or soft matters inside the solution. I'll be describing a model which I tried to develop to understand the polymers which are diffusing through the lattice and some of the interesting aspect of if we have anisotropy in the interactions in terms of, so what are the nature of the morphology of the structures which are getting, and I will conclude and some of this. So we can see interfaces in different variety of system. For example, if you look at dewdrops on the window, viscous fingering, or the bacterial growth, or burning paper front, or bead deposition, thin film deposition. So you have interfaces, but as you know, these interfaces happens in different length scales. But these interfaces actually follow a common universal scaling relation, and these interfaces can be actually in principle we can develop models, and there are models which can able to simulate and model such interfaces in the system. See, one such model I am restricting towards on diffusion limited growth model. So how it is that you suppose particles are diffusing through the solution. So you can, these are on lattice simulations. So you take a particle at the center of the box, then from the very far from the center of the box you try to release the particle
and it can have a random walk, and as soon as it reaches to the seed particle, it becomes the part of the cluster. So you can see that this is some sort of non-equilibrium systems where the interactions are much higher than the actual thermal energy available in the system. So these are a variety of examples where such system can be modeled to what are called diffusion limited aggregation growth models. See, some of the important characteristics of these are, as the system goes on, I don't have the pointer here, the system look, they are fractals. As you know, this dimension is, in the 2 dimension it's less than 2, they are open structures. So I do collaborate with a lot of experimental group. In your system, if you can see such type of dendritic structures happening, there is actually a diffusion limited aggregation growth happening inside the system. So now we consider the system has an isotropic potential. If we have an anisotropy in the system, what can happen? So we published 2 papers on where if the interactions are in an orientation dependent, we saw that there is some critical value of P below that system goes to some sort of absorbing state where system will be stopped. And if the interaction site is larger, then you can see that the system will keep growing, and that is what is called the active phase. And this is what is called the phase transition inside and non-equilibrium systems. So now I ask the question, so what happens if you have polymer-like system? For example, if you have different monomers attached together, and individual monomer can have different interactions. So what can happen, and what is the nature? That was a basic question I asked in this problem. So this is one of the example which is published in this paper where they show that if this is the human amylin, which is a protein, so where you can see that depending on the increase in the pH, they have shown that the structure become more fractal-like in the system. This is an experimental work which is reported. So I assume the polymers something like connected with the different monomers where you have 3 and 4, and I also for the 4 you can have different isomers in the system. So you take at the center, you start with the seed particle, you release the polymers from longer distance, and they try to diffuse and become the part of the aggregate. We assume that the system is non-equilibrium. So now this is some of the snapshots which from the system. So you can see that the system is more open if the length of the monomer polymer length, if you try to increase it. So I tried to look at this and some sort of preliminary study. I tried to look at the fractal dimension. So you can see that as you increase the number of monomers, the fractal dimension keep on decreasing. That means in the system you can have an large open structure which can have an porous kind of aggregates you are going to get. So now suppose you have an anisotropy interaction. For example, one part of the monomer is an hydrophobic and other is just a neutral. What can happen? This is another question I asked in the problem. So what we observe is that if the red indicates that red is going to have some sort of attractive interaction, now you will get an somewhat compact structures compared to an open structures which we got if both are attractive sites. So if we try to look at the fractal dimension, we understand that if we have anisotropy introduced, it will be little more compact compared to both are isotropic interacting particles. So now I ask the question, what happens if we change the interaction sites? If suppose we have one site or 2 sites, depending on where the interaction is going to happen. So what is actually going to happen? Let us see. So these are some of the interesting diblock copolymers and different structures. You can see that they form what are called micelles inside the system. So you can have all the hydrophobic regions coming together and form an interesting structure. So now I try to develop a system of understanding these models in the system. So you start with the head part is actually interacting, and other I consider to be neutral. In principle, you can take the intake. There is no repulsion between red and green, as well as there is some sort of attraction also you can take, or not attraction also you can case. So you can see that if the interaction points are well defined, in the positions are well defined, you can see that toward the right side of the presentation, you can see that it's some sort of micelles which are occurring, and system is under some sort of absorbing state. System will never grow. But if you have interaction sites at 2 sides, you can see that systems start to highly open structures we are going to get. Then here I plotted the number of particles absorbed to versus time. You can see that if both interaction sites are at the two edges, the system start to grow. If we are in the only one site is there, you can see that system undergoes some sort of absorbing state where the system is stopped growing. Here I plotted growth rate versus T. You can see that when you have only one interaction site, system keeps stop growing. But if you have different positions of this interaction, you can see that system keep on growing in that direction. So that means what? If you have a long chain and you have interactive sites are at different position, and number of sites is going to depend on the structure of the aggregates. Here you can see that this is an really interesting and first time observation of such systems. If you try to increase the number of interacting sites, you can see that system can go from an absorbing state to an active phase, and this is the signature of non-equilibrium phase transition. And we are yet to, I would like to work on this problem, and let us see what kind of phase transition is going to observe in such systems. This is one paper I have observed that if you have chitosan and AgNO3 complex, you can see that there is some sort of aggregates which are happening. Such system can be idealistically modeled by what I was trying to propose, and we can see that these structures are almost similar. And I am not telling this exact, but we can try to understand that there is some sort of anisotropy in the system in that particular systems. So in summary and conclusion, I tried to model a system with anisotropic interaction. So in the case of isotropic system, we have a long open structures, but as you increase the number of sites in the position as well as increase the number of sites of interacting sites, the system can evolve or not evolve. Either it can stop growing or it can go into an active phase. So our study shed some sort of some idea about aggregation mechanism if you have a long chain molecule with some kind of anisotropic interaction. So I'd like to thank our principal and head of the, and some part of the computational work I was doing as a in Indian Institute of Technology, Bombay for the computational work, and thank you very much.
Thank you, that was a nice presentation. Any queries from the participants? Okay, there are no queries. From my side, I just want to ask you, this is your PhD work, right?
No sir.
This is your project.
I completed my PhD and now I am working, so it's a part of my...
Okay. Right in the beginning itself, you told that you have chosen the DLA method. DLA model.
DLA model, yes.
Why you have stick on to DLA models? Have you tried the other models also?
Yes, we have already published a paper on ballistic deposition growth model.
Okay.
And where if you have thin films, for example, if you are growing thin films from the substrate, it can be modeled by ballistic deposition growth. In that system also, if you have just one monomer, just I mentioned in this, for example, yes. So just like you will get a critical patch size. For example, if interaction is orientation dependent, if orientation is small, then you will get an suppressed growth.
Okay.
So in the case of experimental systems, if you have vapor deposition coming over there, and you assume that some species can stop the growth of the aggregates, maybe you can think of modeling such systems through this kind of this thing.
Okay, and one more thing also I just want to confirm. You told that micellar formation that is found only in DLA models only, or you can see that in other models also?
Because something happening from the substrate, you have one dimension plus one dimensional growth. Okay. So if it is in a one dimensional growth, the first initial layer will be, see, all the red will be sitting towards downward, and you will get some sort of, in the case of cell membranes, you can see that hydrophobic, so you will get a bed-like structures.
Okay.
If it is one dimension. But two dimensions, since interactions are, for example, if you place hydrophobic material inside water, you can see for entropic reason they will come together. So this is for two-dimensional system, but yet we can develop for three-dimensional.
Three-dimensional also.
Yes.
Okay. Thank you. That was a nice presentation.
Yes, sir.
Thank you, sir.
Thank you very much.
The next participant, OPESC 37, Mr. Nishant. Abhinav, Mr. Abhinav? Illa. Mr. Abhinav? Illa.
Good evening to everyone. Myself Nishant, pursuing PhD under Dr. Arun Prasad in VIT Vellore. Today I am going to present a topic, electrocatalyst for efficient hydrogen generation in hybrid water electrolysis. Introduction. Hydrogen fuel is a promising alternative energy source with zero greenhouse gas emission. It is widely available with high energy density. Water electrolysis. Hydrogen can be produced by water electrolysis, which split water into hydrogen and oxygen using electric current. This process emits with zero greenhouse gas emission. Electrocatalyst. To make an electrolysis, water electrolysis, more efficient electrocatalysts like platinum and iridium are used. These reduce the energy need of hydrogen and oxygen evolution reaction, but they are most expensive. The hybrid water electrolysis approach is also studied for further reduce energy cost in hydrogen production. Aim to develop the highly effective electrocatalyst with exceptional stability and low over potential with cost-effective method. Material and synthesis. I am going to prepare nickel molybdenum sulfate with carbon. This is two-step hydrothermal process method. First, carbon sphere was prepared. Carbon sphere prepared from glucose. Second method, the prepared carbon sphere was mixed with nickel chloride hexahydrate, ammonium molybdenum oxide, thiourea. It kept stirring at 30 minutes, and after that, it's sonicated for 15 minutes. It under hydrothermal reaction 180 degree for 12 hours. After that, the prepared solution was washed with ethanol and water and dried for overnight at 80 degrees Celsius. The prepared material was nickel molybdenum sulfate with carbon. Result and discussion. This is XRD pattern. XRD pattern was well matched with nickel sulfate J-shapes code number 000110099 and molybdenum sulfate code number 0107515339. Same image of carbon sphere. A is the carbon sphere, B carbon sphere along with rods, and C and D are nickel molybdenum sulfate with carbon nanocomposite. F is same image of nickel molybdenum sulfate, and below the XPS spectra, nickel 2P, MO3D, S2P and carbon 1S. This is a TEM image. Nickel sulfide usually attain d-spacing 0.24 nanometer, whereas molybdenum sulfide 0.62 nanometer. Here we obtained d-spacing of 0.648 nanometer. This is the difference because of nickel sulfide was doped inside. Above the image, we can see the fine image of a nanobar. The electrochemical analysis. LSC curve of HCR performance of synthesis catalyst nickel molybdenum sulfate with carbon in presence of 1 molar KOH. Platinum carbon is the benchmark catalyst, so it is compared with platinum carbon. Platinum carbon over potentials occurred at 68 millivolt, whereas nickel molybdenum sulfate with carbon was 91 millivolt. Nickel molybdenum sulfate was 178, where bare carbon sphere was 286 millivolt. Whereas Tafel plot platinum carbon 38 millivolt, nickel molybdenum sulfate with carbon it was 56 millivolt, nickel molybdenum sulfate and bare catalyst was above. This is the OER performance of nickel molybdenum catalyst compared with ruthenium oxide. In OER per ruthenium oxide is a benchmark catalyst which was occurred at 230 millivolt. It is compared at ETA 10. Nickel molybdenum sulfate with carbon was 325 millivolt, nickel molybdenum sulfate 401 millivolt, where bare GC was bare carbon was 524 millivolt, which is also Tafel plot of ruthenium oxide 54, nickel molybdenum sulfate 62, nickel molybdenum sulfate 76, and bare carbon sphere it was 101 millivolt Beckett inverse. The electrochemical impedance spectra, Nike's plot it was fitted with Randall circuit. The smaller semicircle represent the faster kinetics, larger semicircle represent the slower kinetics. This is a stability curve run for 1000 cycle. There is no much difference between before and after. Summary and conclusion: the synthesis nickel molybdenum sulfate electrocatalyst large surface area and suitable pore structure for fast ion transfer. The prepared electrocatalyst showed promising catalytic efficiency, stability and faster reaction kinetics for HER and OER. Ongoing research is focused on optimizing hybrid water electrolysis process to further enhance the efficiency and reduce the cost. These are the reference and acknowledgement. I acknowledge DST SERP for financial support, VAT for funding and facilities, iNEEBA-2024 for providing an opportunity to present my research work. Thank you.
The topic is open for discussion. Any queries?
Excuse me, sir. Sir, very nice presentation. I would like to give you the small suggestion. Can you please go your XPS data? In XPS data, in nickel 2P, and next one, and the sulfur. XPS. You can just try to check the baseline correction. You can use the Sharley fit instead of linear fit because it's not fitted properly. Thank you.
Yes, sir. Thank you.
Again, the same justification. Can you give me why you have chosen nickel?
Nickel sulfate and molybdenum sulfate both are highly active in water splitting. So I want to reduce the over potential. So I just mixed with and I added carbon also.
So this is the first electrocatalyst what you have tried. You have tried the other electrocatalyst.
No, sir, this is the first
thing you have tried. Okay. Okay. All the best.
Thank you, sir.
Anybody is willing to present a paper? Anybody?
next slide.
Sit down. Leading to another present here. Myself, S. Geeta Lakshmi from Vinayaka Mission, Kirupananda Variyar. From Vinayaka Mission, Kirupananda Variyar Engineering College, Salem. I would like to share my presentation under the title of Sustainable Polymer Composite Material from Banana, Jute, Palm Fruit Fiber, Fabrication and Acoustic Characterization. Based on the following content, I would deliver my presentation. Next. Introduction. Generally, noise which is unpleasant, disturbing, which can distract and harmful. Which is noise. Generally, noise refers as unpleasant, disturbing, and a sound which can distract and harmful to audible system. And along with the air, water, soil pollution, noise pollution is a global issue which can caused by urbanization and modernization, mechanization, which can demanding the noise reduction mechanism. Traditional noise pollution materials which is created by using synthetic material which are harmful to environment. Instead of here we use the fibers which from agriculture waste. It is used as a acoustic resistive material for increasing the material mechanical property by using filler materials. Here the acoustic biocomposite material were developed from using banana, jute, palm fruit fiber which has a more acoustic property to enhance the mechanical property by using fillers which is nano fiber and magnesium oxide with by referencing epoxy resins. Further it can be characterization using further it can be structural characterization by SEM with EDX, zeta potential, FTIR, TGA and application through thermal gravity, electrosurface resistivity and water contact angle. This is a materials and method. First we collect the raw fibers, then chopped into your required shapes. Later it can be treated through alkaline treatment in 5% of NaOH, magnesium nanoclay which is a fillers and which can be mixed with the epoxy resin to make a filler and filler resin mixtures. Through hot press compression mold to spread the chopped alkaline treated fibers in this and pour the filler resin mixture in that mold, then compressed in a 1500 PSC for honor. Later it can be post treated and we can get a fabricated acoustic biocomposite material. First we can analyze the mechanical property through tensile, fluxual, compression, ILSS, impact and water absorption. For structural analysis, SEM with EDX, zeta potential, FTIR, TGA, DTA and DSC. We can analyze the potential application through thermal conductivity, electrical surface resistivity, water contact angle. Next. Here we show the fabricated material we formulated in a three different formulation. A shows a formulation 1, B shows formulation 2, C shows formulation 3. Next. First we analyze the mechanical properties based on 6 different mechanical characterization variables. In each sample we take 2 sample pieces which is mentioned as 1.1, 1.2, 2.1, 2.2, 3.1, 3.8. By comparing the average, the sample 1 shows a more mechanical property, so it can be further used as a further characterization. Next. Some which is used for characterizes the morphological surface morphology. In figure A to E indicate the surface morphology with irregular, safe and rough surface which can which indicate the acoustic property and sound damping. E, F, G, H figures shows the elongated fibrous structure which suitable for a sound dispersion, and I and J demonstrate the porosity which helps to sound absorption property. Next. Generally EDX used for analyze the elements which is present in the sample. We use 4 different spots to search this. What are the material present in this what are the elements present in this material. From this we can get a result of maximum carbon. It indicates it shows a carbon which is an element which is more abundantly present in our sample, followed by oxygen and magnesium, gold, niobium, chlorine, which are also element which is present in our material. Zeta potential, which is used for analyze the electrostatic force. In this graph, it shows the sharp peak, which is nearly to the 0 millivolt, which indicate the most of the particles are in the neutral charge. The mean zeta potential of 0.7 millivolt, which indicate the most of the material have a minimal electrostatic charges. FTIR, which is used for analyze the what are the functional groups which is present in this. From this result, we get the alkaline group, aromatic groups, hydroxy group, hydrocarbons, and polysaccharides, which are present in our material, which indicate the our material shows a more mechanical fluctual strength, and also it indicate that we add some fibrous materials also. It shows the polysaccharides also present in our material. TGA, DTA and DSC. In TGA, which is represented by blue curve, DTA, which is represented in red curve, and DSC, which is represented in green curve. TGA, which is used for the mass, which is used to analyze the mass loss. Up to 100 degrees Celsius, it is stable with moisture evaporation. It can reach, it can upstand with 200 degrees Celsius. Then from 200 to 400 degrees Celsius, it start to mass loss is increases because of the presence of organic material. Above 400 degrees Celsius, the mass loss can be reduced because of presence of inorganic thermal residue materials. In TTA, which is represented by the red curve, which shows here the decomposition rate from between 250 to 350 degrees Celsius, the decomposition rate takes place. The maximum decomposition takes place in 300 degrees Celsius. Later it can be reduced. In DSC, it can be represented into the green curve. It shows that the element should be endothermic or exothermic process. In our material, which shows a endothermic process, which shows a energy absorption, thermal energy absorption. Thermal diffusivity and conductivity, which is used for analyze the how much ability to conduct the thermal energies, which can both the curve can shows a similar ranges from 40 to 120 degrees Celsius. It shows a optimal heat transfer. Later it can be reduced. Water contact angle, it can use to analyze how the water droplets can interact with our surface. In this result, we can get the contact angle of 96.6 degrees Celsius. It shows here hydrophobicity. If materials is more than 90 degrees Celsius, the contact angle result should be 90 degree, more than 90 degree. It become a hydrophobic nature. So it can be used as, so our materials can be further used as a water repellent material. Electrical surface resistivity, which is used for analyze how our material can react with strongly resist the flow of electric current. We standardly test at the 100 volt. As the result, the value of 161.25 megawatt, we get a resistivity range is relatively high, which indicate the our material is good electrical conductivity. Further, we can give an analysis for imbalance test to confirm our acoustic property. I can conclude that in our conclusion, our project in our project we successfully developed the acoustic biocomposite material from agriculture waste by using a banana fiber, jute fiber, palm fruit fiber to enhance the material property through using fillers, which is a nano clay and magnesium oxide. we use a nanoparticles for to give more enhancement for our material and reinforcement by the epoxy resin. It can be used by using a local sources biodegradable materials and which can be economically available and eco-friendly to the final production materials which can be used as a thermal resistivity material, electrical resistivity material and water resistant material. We can further analysis for aquatic material to confirm the confirmation for that if the material can also resist the aquatic material. Our material can be used for our insulation for house, whatever, where the particular criteria needed, we can use our material for that places. These innovative approaches contributed not only for the environment sustainable but also give an effective solution for a noise control to further advancement in the green composite material for the aquatic application. Based on the, we use this reference for our project. Thank you.
Thank you for the presentation.
Thank you.
Any queries from the participants? Is this your project, ma? Which year you are now?
It's a final year.
Final year.
Biotech.
What department?
Biotech.
Biotech. Okay. From my side, I just want you to ask you two queries. You were telling that this is having hydrophobic property and TGA, DT, all this you have proved. My question is, how far it is a biodegradable product? Is it eco-friendly?
Compared to other resins, epoxy resins can slowly degradable, but the other fibers and fillers, magnesium oxide also can degrade. Once the epoxy resins can degradable, but it can take long time. Compared to other resin, it can definitely degradable. Once the resin degradable, the fibers and the filler also degradable, but it take some durations.
If at all you want to come up with a viable product for acoustic, what product you are planning to come with the product?
Sure.
Acoustic. You told it has acoustic property, right?
So we give a characterization for the acoustic property through impedance tube test.
Okay, thank you.
We didn't get the result now, sir.
Okay, thank you. Good presentation.
Thank you, sir. Like the session is over and we will meet you on tomorrow morning. Now I request our principal sir to honor the jury of the session. May I invite Dr. V. Anbalagan sir to honor the jury of the session.